All right, so welcome everyone after lunch. I did not order the drinks that you can stay in, but hopefully this is as interesting as going out in the city. I'm Avishek. I'm from TU Delft, an associate professor there, and my work is mostly on explainable information retrieval on complex knowledge intents, complex question answering, and I also do a little bit of neural information retrieval. But my talk today will be about information retrieval and explainability issues. Okay, so I want this also to be a bit more interactive. So if you have questions in between, raise your hand, don't be shy. We might not get to all the content, but that's okay. That should not be the excuse for not asking questions. All right? Good. So this does not work. All right. Okay. Now I don't have to preach to the choir in some sense, right? So everybody knows that, well, we have a huge revolution in some sense going on with the advent of the large language models. The models are going larger. We see great performance in natural language processing tasks. We see a great improvement in IR tasks. Think about ranking, think about question answering, and so on. But one of the major problems which people face now is whenever they use these models, people do not know if they can trust these models. Okay, so which means that, well, if you cannot trust these models, you do not know whether they're right for the right reasons, right? So if you have somehow a machine learning model which is trained on some supervised data, and you see that it has great performance on your training set, do you really trust that when you deploy these models in the live scenario, will it fail? Will it make embarrassing mistakes? Does it pick up all kinds of strange correlations, all kinds of strange shortcuts, or does it actually do what is required of it? Okay, so that's the main reason why we need interpretability or explainability. To give you a very sketchy definition of explainability, as in the literature, is explainability or interpretability is the science of finding the why behind a decision and conveying it to people, users, or humans in a way that they can understand or comprehend. Right? That's the very sketchy definition of interpretability. I'll make it more concrete as it applies to information retrieval a bit later, but this is the operational yet sketchy definition. The output of interpretability is an explanation, right? And explanation can be in many forms, can be for many people, and we'll see what kind of explanations are there and what can we do. Now, the first question is that why do we need interpretability? When do we want to use interpretability? And what does it actually mean? So consider this canonical task that everybody knows, the document ranking task. You have an intent, you write some query words, which is a small compressed form of your intent. From a million or billions of documents, you kind of get a small selection, and finally you rank these documents, right? This is the ranking task. Everybody knows about this. And it's fair to assume that many people use contextual models or deep learning based parameterized models or over parameterized models for this ranking. Okay. Now, why do we need interpretability? So let's say that you have this query, keyboard rankings, and on rank 1, you have this. And if you add this term acceptable, I'm just adding a term acceptable to the beginning of this document, the rank 1 document, what do you think happens? Or what do you think should happen? What did you expect this to happen? This is just a BERT ranker, which is fine-tuned on, let's say, your MS Marco data. Umang is sitting here, right? Yeah, it's server, by the way. What happens? What do you expect? Do you expect the ranking to change a lot? Do you expect the scores to change a lot? Who says that the score should change? Who thinks that should change, right? Should change. To the positive or the negative? should the score decrease? Is the relevance of the document impacted by the term? Should is different from what you think might happen. The relevance should not be impacted in some sense, or not drastically at all, right? Now, what actually happens is there's a big drop in the rank. Actually, there's a rank drop of almost 20 positions in the rank list. And this is by far not the only example where there is a score drop. So we did this experiment. Your mom is right there. She did this for lots of pieces. And for all these queries, when you add the term acceptable in the beginning of the document, you saw huge score drops. We did similar experiments where we added certain terms to the bottom rank document. Think of this as the 100th rank document. And there was a big score improvement for these documents, right? So you really do not know what these models, what the decision making of these models are internally. Yeah? Question?
You say that it should or should not drop.
Yeah.
With the ground truth data that you say.
There is no ground truth data for it, right?
How can you say that?
But if you think about what model should do, right?
I mean, what do you think and what happens in reality?
It's different. That's why I say, right? What should happen and what happens in reality are two different things. But if you look at the axioms of information retrieval, they say that a term which is probably not relevant to the query should not impact the ranking of the document. What actually happens is, of course, a different thing, right? So we are now looking at what is actually happening.
So my question was something like, let's say you add acceptable in the front of the document.
Yeah.
And does it mean that, you know, our users are going to click on it with the keep data less or?
So what would actually happen if you added the term acceptable and your sub results are only 10, right? Nobody goes to the second page. This is the most relevant document, and for some reason you will never discover this document, right? Right? So
It's changing the document, adding this term acceptable.
It's an academic experiment. It's an academic experiment. There are experiments which you can do where you can add the term acceptable in the middle of the document where it is more natural. But it is of interest for people that just by the existence of some mere terms impacts the relevance of the document for queries which, you know, you should be performing good on is a matter of concern, right? Now, well, why is it interesting? So there's another question.
I see that there are some authors that divide separate explainability from interpretability. Is there by any reason are they equivalent or?
Hold that thought. You will see this in 5 minutes.
Okay.
Okay. Okay. But let me kind of get on with the motivation and we'll come back to that. So now, well, let's have this, let's try to see if you guys can answer this question. Where is the world's largest flower garden? People who already have seen my presentation know, but people who have not seen this, what's your guess? Where is the world's largest flower garden? Sorry, Teutonhof? Good, but it's not that. No, unfortunately not. Countries. Any other guess? One more guess and then I'm going on.
UK?
UK? No, it's not in Europe.
Brazil.
Dubai. Okay. Now, how did I actually come up with this one? So essentially what happens is you do a retrieval round, okay? And then you have a closer look at the top few documents, right? In most of the cases, people look at the top document, but let's say that, you know, you look at the top 3 documents and you try to answer this question. So a retrieval round is very important in many of the knowledge intensive language tasks, right? So question answering is one of them. The same thing happens in fact checking, right? So you want to actually check the claim if the Bay Area has any towns or not, right? This is clearly wrong. And you do a retrieval round and you find evidence that this is indeed not true. Okay. So what interpretability can also do for you is you not only want what the decision is, in this case, it's an incorrect claim, okay? But you want to zero down to the evidence, what caused the model to decide for or against it. In this case, it is this sentence in this document which was stopped right. There's something which might help the people or the fact checkers who are playing with this or using this. Okay. Well, these are not two isolated examples of knowledge-intensive language tasks. There are many. Okay. If you want to add citations to Wikipedia, well, you do a retrieval step and then do the same thing. Same thing with conversational AI, same thing with knowledge-based construction and so on. Okay. If you're interested in question answering, this is something which I also work on. And I was telling Mohammed that I finally made my website after 2.5 years, right? Go and visit this, right? We also have a book written on this one. Don't read this book. This book is already outdated in 2 years, right? But the other benchmarks, you can still play around with them. All of this is retrieval is the first step, and then you do question answering or fact checking later on. Okay. Now, what is the general recipe or a solution framework for all these tasks which are booted up by retrieval? You have a first step retrieval, which is done by a ranking model or retrieval model. And then you have a task specific model, which is specific for all these knowledge intensive tasks. Okay, think about knowledge construction, QA, and so on. Okay, and it is fair to say that all of this has been bootstrapped by deep learning based contextual models, right? So you have RAG systems where this is dual encoder models, right? And you have more monotype, BERT-based fine-tuning in the task model, or sometimes even LLMs now. And the question is that all these models are somehow complex and non-interpretable. And that's why we need interpretability. So one operational reason to go one level further about why we need interpretability is not only do we need models that give us correct results, but we want them to be right, but for also the right reasons. This is very important. Other reasons you might have heard a lot, people who work on interpretability, is you would want to kind of use these insights to discover some new science, right? New properties of information retrieval, which you did not know previously. We'll come back to that a bit later. You also need to improve trust and legal recourse, right? I'm not going to go into the philosophical debates or how they're kind of finally resulting in these two things. Kind of models are called interpretable by design models. It's arguable whether they're interpretable or not, right? Imagine this decision tree becomes huge, then, well, I don't know if it is interpretable or not, but with a little bit of effort, they're still interpretable, okay? But usually these models have a problem with accuracy because they don't have enough parameters. They don't have this flexibility or expressive power to model each and every complex relationship, all right? Then you have, what? Yes. So this is the right place where I answer your question. People use explainability and interpretability almost interchangeably. And there is a reason for that. And some people like it, some people don't. So usually explainable methods or explainable by design methods are referring to these models, interpretable by design models. Okay. And this is a terminology in the machine learning community. They are explainable models, meaning they're interpretable by design models. And in some other communities, people say explainable models are for the user and interpretive models are for the developer. Meaning that, well, if you're reading off a decision tree, that is more for a developer, and you come up with an explanation or an interpretable output, and then you convey this interpretable output in a natural language. This natural language output is called the explanation. So in some sense, there is no consensus in the community what kind of models you should say are explainable models, or what kind of models you should you say as interpretable models. But for the sanity of information retrieval, let's stay to this terminology that the models, the interpretability is kind of a systems perspective, and on top of that is the user perspective, which is called explainability. Fair? So the output of a approach that we're going to kind of see will be the explanation, and how you convert that explanation and give it to a user is starting under explainability. So explainability is kind of overarching. Question?
Yeah, so we are assuming that a problem is understandable for users. It implies that it can be understood by a system, because
so interpretability is always devised to explain the model to a user, never the other way around, right? So there is there's always understanding of the model to the user. You don't explain anything to the machine, right? In this sense, the explanation is always for a stakeholder, for a human. Okay. Good. So what questions are we interested in? So the common kinds of questions you might be interested in is in figuring out which features or which training instances or which parameters are responsible for a given decision. Okay, so you have a trained model and you want to figure out which features are responsible, which data points are responsible, right? So these are all the kinds of explanations that you can have. Or in information retrieval specifically, you want to ask questions like, why is one document ranked higher above than another, right? That's a standard ranking task. Why do you not rank another document which is ranked 20th and to rank position 2 and so on? Or you want to characterize, well, the model has learned something. Does it adhere to the rules which have been invented, discovered in information retrieval, right? And people who know a little bit about axioms in information retrieval, you want to figure out if models actually adhere to the axiomatic rules which have been invented in IR. Okay, but well, is there one interpretability? Of course, the answer is no. Interpretability depends upon who you are giving the explanation to. So it really depends who your stakeholder is. Are you explaining to a model developer? Are you explaining to the end user? In this talk, I'm going to focus on the explainability to the model developer or somebody who knows his or her way around complex systems, okay? Usually in the Chi community, people focus on, well, you got some explanations, right? How do you kind of translate this to the end users, right? It requires a bit of requirements engineering, speaking to stakeholders, right? There are also different kind of approaches and different kind of explanations. So the different kinds of explanations are the following. So let's think about what kind of explanations you would want to actually give to a user. The explanations could be in the IR context. You could say which of the terms are important, right? And the output that you're looking for are somehow called term attributions, heat maps, saliency maps. There is a lot of word salad going around, right? But all of them mean the same thing. When you want to figure out which of these words or terms are impacting the decision, a green here means that they are impacting, red means not impacting, or white means they're neutral, right? So the degree of greenness means more impacting. So these are called attributions or feature attributions. Then you have free-form text. I'll come back to the example later. There's free-form text. You want to figure out which of the words or the terms are responsible for a decision, but for the entire ranking list. I don't want to what degree in a document some words are important, but overall, what was the model's perspective or model's understanding of the query, right? And when I say this, think about query expansions. What happens in query expansions is you have a query, and the model internally, explicitly or implicitly expands this query to improve the understanding of the model and hence ranks the document. You can see on the free-form text explanations of the terms which the model actually is internally expanding the query. Okay, so these are the other kinds of explanations. Now, how can they be used? You can use these feature attributions in the following manner. You can compare different ranking models. For example, in this example, you have the question or the query, how to find the mean, and you have a document explanation as the following. And you can see that ranking model 2 is focusing on the other word sense of mean, being the mean person, mean girl. And there, the first ranking model is focusing on the mathematical word sense of the term. Yeah? So these are some of the ways in which you can use explainability tools or interpretability tools to maybe debug the model. Okay. This is not systematic, by the way. You have to do this manually, but that's another question. But if you had these tools, these are some kind of comparative tasks which you could do. Okay. What are the other kinds of explanations? A very common form of explanations, and this is coming from natural language processing, is called extractive explanations, meaning you would want to figure out what part of the document, okay, was responsible for a document, for an explanation. Not in the word sense, but essentially, what are the summarized or extractive summary of a document which is responsible? This is extractive explanation. So these are the three kinds of explanations which you can have, okay? Now, what is specific to information retrieval? In information retrieval, you have a different scenario than standard machine learning regression models or classification models. In machine learning, you are almost always interested in what I call as point-wise explanations, right? A point-wise explanation is you given a query document pair and you are asking, why is this document relevant? Give me these explanations. Why is a certain document relevant? In this case, there is only one prediction. You're predicting the relevance of a query document pair, right? And usually in machine learning, this is always one classification. Is this image relevant or not? Is this image correctly classified or not? In ranking, however, you're looking at a set of decisions in a given ranking, right? So you're interested in these questions, why is one document more relevant than the other? Okay, or you even have list-wise explanation. Why is this top part of this ranking relevant at all? Meaning you're not trying to explain one relevance assessment or one relevance estimation. You're trying to explain multiple predictions here. Why is D1 greater than D2? Why is D2 greater than D3? And so on. Okay, so it's a slightly more complex task than doing point-wise explanations. And that's one of the reasons why in information retrieval, explainability is slightly different from vanilla interpretability in machine learning or natural language processing. Clear? Questions at this point of time? Okay, so now that some of the notions have been set in stone, let's actually go to some of the approaches in explainable IR. Well, I told you that there was one kind of explainability, which is explainability by design or interpretability by design models. The counterpart to this is called post hoc interpretability. So explainable models by design or intrinsic interpretability is during model building, you ensure that something is interpretable by design during while you're building the model. This might be because you choose a certain model family like decision trees, or you do something which I'll talk about this something a bit later on. You do something where the explanation comes as a byproduct of your prediction. Okay. The second part is post hoc explainability. You don't care, you don't want to compromise on your model quality, right? So you're, let's say, an e-commerce site. I want my CTR. I want the best and the fanciest model, and I don't want to compromise on utility. But what I do want later on is, if it's possible, I want to figure out what the model means, but in a post hoc manner. You can probe the model after the model has been trained to whatever, I don't care. And this regime of approaches is called post hoc interpretation. Good. Now, the third kind of interpretability is holistic interpretability of the model. Understanding the model in itself, because in the previous two situations, you were conditioned on interpreting a given decision, right? You have a query, you have a ranking, and you have an IR model, and you want to focus on answering the question only about the ranking, right? It's very local, right? But if you want to understand the model in its totality, you would want to actually understand, does this model understand world knowledge, right? Does it know facts, which helps it do better in a ranking task? Or does the model understand document term matching or BM25? Does it actually understand that, right? Or does it actually understand IR abilities as understood in IR axioms, right? So, these kind of approaches are called global approaches. So if you want to know a little bit more about the taxonomy, we've written this nice survey, which has been there since 2 years. You can have a look at this. What I want to focus on is on the three major families. The first one, the post hoc methods, and I'll go then to interpretable by design and grounding if I get time. Okay. Any questions about the notions at this point of time? Good. All right, so let me go to post-hoc interpretability, where I don't want to compromise on my model quality, and it's very local, meaning I want to explain only one prediction. Namely, here the prediction is that I have a query and I get a ranking, and I want to explain this ranking. Right? So the idea is the following. If in the best case, what you would want is you would want a model which is simple enough. I can read the parameters, I can read the weightage it gives to some terms, and then I'm done, right? This is what you want, right? Nothing of this sort actually is possible given data-driven science and parametric models. So what you want to do is that when you do not have a complex model and you cannot explain a globally complex model, you can make local approximations. What do I mean by this? So let's first look at the two kind of explanations which you can expect out of post-hoc models. You can expect either feature attributions, think heat maps, or free text explanations here. Now, before I go on to the method, let me first set up the rules of the game. What is a good explanation? So firstly, a good explanation should be accurate, meaning it should find the right reason behind the decision. People who work in recommender systems should know that there is a lot of work on explainability, but most of the explainability work does not focus on the accuracy of the model, right? It's an extremely difficult thing to figure out if the explanation really explains what the model's decision-making process is. It's very difficult to establish that. And most of the research goes into making sure that this happens, the accuracy. The second is called fidelity. This will become clear in 2 slides, but think of this as if you have another model, a simple model explaining a complex model, then the simple model should be faithful around the decision point. Because these are all local methods, you should make sure that whatever explanation method is should be faithful around the locality. Small perturbations to the input, this input point should not actually change in big differences in your explanations. This is very important, right? This is for the stability of the explanation. Goes without saying that the explanation should be understandable, otherwise this is not an explanation. What do I mean by understandable? You should use natural language terms at least, like words, phrases, extractive stuff, and not give me values of parameters, right? That's not an explanation. And finally, the explanation model that you use, the approach which you use to explain should be also simple enough. So these are the rules of the game, that you want to have a explanation approach which is accurate, faithful, and should give out explanations which are understandable, right? Now, how do I do this? So I talked about these two kinds of explanations, local explanations and global explanations. Local explanations are when you're explaining a single prediction. Global explanation is when you're predicting for the entire data set, all right? With this in mind, we'll focus only on local explanations here. So what you have a simple classification problem. I'll build this up to a ranking task, but for now, this is a suggestive example, okay? You have a classification problem, and if I have to do very well on this classification task, my model looks something like this, okay? It's a complex model, but what you would want is a simple model, right? A line is a simple model because few parameters, you can explain this. But you cannot have a line which will give you the accuracy you want. No, that's just not possible. Right? It's just not possible. So global approximations are hard. You cannot come up with a global approximation to this data point. But what is possible is local explanations or local approximations. Now, what do I mean by this? So let's say that you have a query, okay? And this query is not the whole line, but a small part of this line, right? So maybe it's that part. I see this here. Yes. If you zoom into that part, the local decision, it almost looks like a straight line, no? So what is possible is you can come up with a simple model, aka a small or a straight line, which is approximating that region of the query. And these are what is called local approximations. Now, how do I solve this problem? What do I do? is I compute or collect a small local data set around that query point. Okay, so think of this as you sample some points in the region of the red box, some of them are positive, some of them are negative. And after you've done that, you can learn a machine learning model where that is a training data set, right? So these are explanations which are based on local sampling methods. And the first method to start off the entire interpretability work on post-hoc interpretability is called LIME. Okay. Now, LIME in a nutshell is collect a local data set with a small epsilon neighborhood. Note that the labels actually come from the original classifier here, the actual prediction. And the second step is just train a classifier. Okay. And that classifier should be simple enough. Questions about LIME? Yes?
But if the classifier is not a problem, it's for a decision tree. So how to translate this method?
So it really does not matter, right? If it is a line or a tree or a neural network, all it means, all you need is, given the query, you should be able to sample points in the region, right? And you get the labels from the model. How you get the labels, how is it parameterized, you don't care. As long as you get good labels, that's good, right? So the quality of your explanation is as good as your sampling strategy in some sense, right? You should be very close together, close to that, and should follow the rules as I told you. Yes?
What if all my samples are centered out, are actually in segregation? So can they
One label.
one label?
Yes.
And they explain.
By sampling. By sampling. Right? We come back to sampling, right?
Yeah.
So a lot of effort actually goes into how do you actually sample so that you get enough evidence either side of the line. Okay, good question, right? Because you can, of course, you always want a closer epsilon neighborhood, but well, if you get labels, then maybe you have to increase the neighborhood. It's one heuristic.
Classification from terms of 1 to data from like the response generation.
Yeah, so there are many extensions to this. We will see how you can extend the classification problem to a ranking task, right? But there are many extensions to this. Okay, so this is a suggestive example for a classification problem, but you can extend this to many other problems like text generation and so on. But if you think about it, right, the text generation problem is actually an extreme classification problem, right? The next word is one among millions of words in the vocabulary. Okay, so it's an extreme classification problem. Good, good. I just don't want to miss out on a lot of interesting thing. So the first idea was, well, let's just try this thing. This was a short paper, right, in information retrieval, is, well, how do you do this for ranking? And the first immediate idea, which any of you can also come up with, is think about point-wise explanations, right? Forget about all the multiple explanations or multiple decisions in a ranking. I just want to explain why is the query document pair relevant, right? And to do this, you collect a local data set, again, the same LIME method. Now the question there is, how do you create these small perturbations as it was asked, right? How do you create these perturbations? Because you're dealing with text documents, let's say, right? We're looking at text retrieval here. What do these small perturbations to a text document look like? That's the first question which we have to answer. Well, once you kind of have the perturbations, right? What is happening? Yes, this is what I want. Too many animations.
And close the small
This is a difficult thing because I have to go to a different screen and it does not allow me somehow. I'll try to go along with this one and hopefully it's, no, I cannot go to the next screen. Because if I cancel this again, the sharing problem comes up. So I don't, what is working, I don't want to break. Sorry about that. Right, so the second question is that, well, we'll somehow learn about how to create these perturbations. The second question is, what is a simple classifier here, and how do we interpret the results of this classifier? These are the two questions, right? If you have to adapt a local approximation method to information retrieval, or in this case, a document ranking task. Now, how do we do perturbations? Now, you're given a query and you have a document, and this document can be perturbed in the following way. You randomly choose terms to drop from this document, okay? In this case, there is some queries which are not relevant to the query. In this case, health hazards, and then you can drop doctors, hazardous, and healthy, which are more relevant. So bad for dropping, that's why they are red. And some words like say and lifestyle not so useful. Okay. So once you do this, you get different documents, and the scores of these documents change given the retrieval model or the ranking model you consider. Right? So there are some sampling methods. There are uniform sampling, bias sampling, and mass sampling methods, right? I don't want to go into the details of the sampling, but once you create these samples, the simple approach or simple model or simple classifier that you use is just a BM25 model, because that's a well understood text retrieval model. Okay. Now, this you can do for point-wise ranking. But the most difficult part and the most closer to what we want are list-wise explanations. That's at the end what you want, right? Pair-wise explanations and list-wise explanations. How do we do this? So this is the most subtle and involved part of the talk. So if you don't understand, please ask me again. What you have is you have a model f of q that you want to explain. Think of this as a BERT model, right? BERT fine-tuned model. And it gives you this document order, D1 greater than D2, and so on. What you want to do is you would want to explain this using a BM25 model or a simple model, okay? And you can figure out how good your explanation is by looking at how close these two ranks are, and basically taking a rank correlation between them. Okay, so you're good if the two explanations, or sorry, the two rankings have a high rank correlation. Now the question is, how do I create a close enough or a high rank correlated output, right, by using a simple model? I can do this by adding one more degree of freedom to the simple model, aka adding terms to my query. So the principled formulation of this problem is, you have a simple model. The only thing which you can do is you can add query terms to your query. What query terms do you add to your query such that the simple model gives you a ranking which is close enough to the ranking in question? Is it clear? If we are clear here, then only I'll go ahead. Is this clear? The explanations are the terms that you add to a query. That's the only degree of freedom you have. And given a retrieval model, which is a simple BM25 model, I want to figure out which query terms to add such that there's a high rank correlation between the simple model and the complex model. Okay, I see people nodding. So this explanation model or the simple model is called a proxy model. Okay. And the explanation is the set of terms that you add to the query. The hypothesis behind this is that the terms which you add to the query, right? So these are the internal expansion terms which the original model is thinking about, right? And hence it ranks the documents the way it does, right? So you are interested in expansion terms, in other words, such that the rank correlation is high. Now, how do we solve this problem? So the first thing is, let's do some document perturbations to get some candidate terms, because a set of terms is the vocabulary, which is in the millions, right? You would rather want a small set of candidate terms which are impacting and then have a closer look at it, right? So the step one is selecting candidate terms. You remove some terms from the document, you add some, you remove some other terms from the document, and you have a look at how much does the ranking score change, right? In the first example, doctors, hazardous, and healthy lifestyle, there's a big drop in the relevance score. Okay, maybe they're important, these terms, right? But if you drop say and lifestyle, there's not a lot of drop. So your candidate terms are those terms which result in a big change in the relevance score as assessed by the model we want to explain. Okay, so after this candidate term selection, you come up with a much smaller set of terms that you want to have a closer look at. These are still not your explanations, but this is, you know, the first step to get a smaller set of terms to look at. So now let's actually come to the list-wise explanations or pair-wise explanations. What you want is you want to satisfy all those preference pairs. Your ranking is essentially a set of preference pairs. People who do learning to rank would actually understand this, right? More that you want to satisfy these preference pairs. On the other axis, you have the terms, your candidate terms. So essentially what you want to do is you want to select the candidate terms which satisfies most of the preference pairs. So this problem is actually called a preference pair coverage problem, right? It's modeled as a preference pair coverage problem. So the value of each part of this matrix tells you how much does this term satisfy the preference pair. A positive value is a good value, a positive value is good, it satisfies this preference pair. A negative value is a bad value. So essentially what you're doing is you're trying to choose these rows, which is essentially terms which satisfy most of the preference pairs, right? This is a combinatorial optimization problem. As with all good things in life, it's NP hard, but then, well, we use greedy to solve this, okay? So, well, this was the first work which kind of give you all these explanations. Now you should ask me, you solve this preference pair solution, right? But, you know, where are the pairwise explanations and listwise explanations? So if you want pairwise explanations, for example, you want to ask if y is d1 greater than d4. Okay, so you focus on only this column and read out the words which result in a positive value. If you need a list-wise explanation, you basically solve this optimization problem, and it will give you a set of terms which covers or satisfies most of these preference pairs. In the beginning, when we did the work first, right? So you got a fidelity of 0.78, this rank correlation. This was reasonable enough, but now we've kind of improved this in future work, right? And this is some of the results which you'd get, right? Those were the days when these were the neural models, the ESM, DRMM. I don't know if you people remember. And we looked at these queries, and the explanations we got were the following. DRMM gave me all the mathematics sense words, and ESM gave me all the other senses. Okay, this kind of, you know, you can use this to kind of figure out under what conditions does one model do better for a given query and so on. Good. How much time do I have? Do I have? No, I have 45 minutes more, right? Good. Good. Now, recent results, as I said, we've kind of improved this. I will not go into technical details, otherwise I'll miss upon all the other interesting things. So, well, whenever you're using BERT might not only look at term matching, right? It might also look at some other aspects, right? Semantic similarity, it might also look at named entities and so on, a proximity between query terms. So using just one simple ranker as an explanation might not be enough. So you can actually extend this paradigm to have multiple simple rankers, which can tease out other factors behind the prediction. Okay, so that actually gives us a large improvement, right? It gives you a more nuanced view about why is one document more relevant than the other. There's another one which is work with Maria here. Unfortunately, it got rejected, but we soon get accepted, I hope. And that's actually using Shapley values to do the same list-wise explanation. As a small interim summary, whenever you're doing explainability methods for information retrieval, it's much easier to do point-wise explanation, which most of the people in the ML community focuses on. Extremely hard to do list-wise explanations, but that's what you should be focusing on. Okay, because you're not explaining why is a document relevant, you're explaining why a set of preferences are relevant. Okay, and that's typically a hard task, right? And there are multiple approach families which we can try out here. Okay, I hope I have kind of given you a slightly detailed overview of how you can do post hoc interpretability, meaning if you have a model and a query, I explain this by giving you some words. Okay, this is the short summary of this. Any questions about post hoc approaches? Have people used some post hoc approaches in the world? Yes, there's a question there.
So you're generating the Shapley, how are you?
I don't want to go into details. We can actually take it offline. This is a very interesting paper, right? I can talk about it offline, by the way. But we can come back to this. If there is time, I can go on. Okay, so let's actually go to the second part, which is interpretable by design approaches, right? Yes?
Shapley value method is the global.
It's also a local approach.
Global also.
Also a local approach. Yeah. Shapley is a local approach. Yeah. So now we actually go to the second class of methods. This is interpretability by design approaches, right? And what I mean by interpretability by design is not always decision trees. The decision trees was just a suggestive example. The problem with coming up with interpretability by design approaches is that you have a trade-off between the quality, meaning how good your results are, and the explainability. This is always a trade-off. So there are multiple interpretable by design approaches. This is almost a big family now. So a small reminder to everyone, whenever there is a paper which claims that something is interpretable by design, does not mean everything is interpretable. There are components of the model which are interpretable. There are components which are not so interpretable, okay? And that's a disclaimer which every paper should have, unfortunately does not have, okay? So when you're reading these papers which claim themselves are intrinsically interpretable or interpretable by design, the question that you should be asking yourself, what part of the approach is indeed interpretable? Okay, so let's first start with some text-based approaches. And when I say text-based approaches, I'm immediately going to jump into transformer-based models. So think about this as you have the following setting, that you have a query and a document, and you give this query document pairs to your BERT model. Yeah, think about the BERT or a monotype model for re-ranking. And what you have is you have feature. This does not have a, what does it? Oh, yeah. So what you have is your feature extraction at this stage, and then you have some kind of feature aggregation for prediction. Right? This is the standard way in which you do re-ranking. Okay. There's another approach family which basically says that I'm going to look at the document, but during training the document, I'm only going to look at parts of the document, not the entire input of the document. And I'm going to only allow parts of the document to go through the prediction. I'll talk more about it later. So there are these two family of approaches, but the green parts there are the parts which are claimed to be interpretable. Not all parts of these models are interpretable. So the question, as I said, to ask is what component is interpretable? And I would say that in most of these approaches, the BERT model is not interpretable. What is indeed interpretable is the inputs and the outputs of this model. Okay? So in a BERT-based model, this feature extraction part is not interpretable, but the output here is interpretable. So for example, you have a query bike theft, report stolen bicycle online, and you drop these words, report and online. So the output stolen bicycle, this is understandable. Good. So this is a lot of animation, which, yeah. So let me actually go on to a concrete example and a concrete model, which will help you understand how these optimizations are done. In standard machine learning or NLP, what do you have? You have a training data set here, and you learn a machine learning model to reduce generalization error, right? That's what you want. Which means that if you have some kind of a text input, like the movie experience was awful, and this is a sentiment classification task, what you want to do is you want to predict whether this was a positive sentiment, negative sentiment, and you use a parameterized model for this, right? This is the standard way of doing stuff. Now, what we are saying is, hey, maybe that's not what you should do. If you care about explanations, you should first try to explain and then predict. Now, what does it mean? Explain, then predict. So think of this as, if this document has to be classified as a positive or a negative review, pick out parts of the document which are indeed relevant for the prediction, right? In this case, hopefully, this part is the relevant part for the prediction, okay? So in the first step, you select parts or you extract parts of the document which are relevant, and then only use that relevant part as input to predict. Now, what's the advantage of this? The advantage of this is that you definitely know that only this part of the input was responsible for the prediction, not the others. And you can claim that this is the explanation. This part, I'll come to the details of this, but essentially, in the explanation part, what you're doing is you're selecting words which are responsible for your final prediction, and you're doing this during the model training process. That's the important part. Okay. And how can you do this prediction of finding out the selected parts? You can use a parameterized model. Okay. So I'm asking you to break down the standard prediction problem from given an input, predict an output, to a two-step problem. In the first step, predict what part of the text is responsible. And in the second part, just use that part of the text to make the prediction. In this way, you ensure that the prediction is solely based on the explanation. All right? And this is a major problem which is unsolved in your post-hoc methods. Because in your post-hoc methods, you might actually get some explanations, but it's very hard for you to evaluate if these explanations are indeed true or not, right? But in this case, you know for sure, or almost sure. So there is now new research which shows that, well, it might also cheat, okay, or our work, right? But at least you know for, at least you're, more or less sure that, well, these explanations, these extracted pieces of text are responsible for the decision.
So, that first part of understanding each part of the input, what are using what
I'll get there. I'll get there. We'll look at the method. Close enough. But yeah, we'll get there. Any other questions? This setting is clear. These kind of approaches are called rationale-based methods. There is almost a survey on this one, right? No. Good. So now, how do we do this? Your question. So firstly, there are two ways to do this. The first way to do this is think about this as selecting a part of text and then trying to evaluating the goodness of this part of text. Okay. Now, you don't have training data in many cases for this part. Right? Imagine if you have training data for that part, then you can just predict, do token classification. Right? You have a classifier in each token and you can predict only if you had the training data for this part. Somebody annotated stuff. We'll also look at that, but let's say that you do not have any training data. So what you typically have is you only have the labels at the end, yes or no. Okay. So this two-step process has this unfortunate problem of having a discrete output here. Okay, and whenever you have a discrete output and then you make a prediction, what do you use? Maria alluded to that problem in the talk before. Whenever there is discontinuity, nowadays you use reinforcement learning. Okay, so you use policy gradients so that you kind of, you have a word model here. Okay, you can have any model, but let's say that you have a word model here. So you try to optimize for this loss, it goes and optimizes for this word model, and then you use policy gradients to go and update the estimation. Okay, so that's what you kind of do. You have a task loss, which is how bad you're doing on the task. Okay, and you have some explanation loss, and the explanation loss is usually defined by continuity, right? You would want to select the tokens which are close to each other or in sequences. You don't want to select one word there, right? You would want to kind of select sentences which are continuous, okay? And then you basically propagate the gradients all the way up to optimize both your prediction class, the prediction word model, and the explanation word model using policy gradients. Okay, I'm not going to go into details about policy gradients, but this is usually a doubly stochastic gradient. Right? So, is this clear? There is also work where you get annotations for the first part. And this is something which you should consider doing in your work. If you're working on a natural language processing task, right? Whenever you're asking people to annotate some data, which is give me positive or negative sentiments, also ask them to highlight parts of the sentences which are relevant. So think about this as relevance assessments in TREC, right? You people typically kind of highlight parts of the text saying that this is the reason why it was predicted in a certain manner. And because if you did this, then you get training labels for the first part here, right? And you don't have to do this pesky RL mechanism to optimize both the models, right? You have training data for this, you train this model, and you have training data for the second one, you train this model, and then you're done. It is extremely easy to train then, and it does not have some other problems, right? Because recently we found out, this is not there here, recently we found out that if you train these models end-to-end using reinforcement learning, the models might cheat. The models specifically will take already a decision here, encode this in the position value or the first value, and then they will cheat through that, right? So it might look like explanations, but they're indeed not explanations. Okay. So the conclusion here or the suggestion here, if you're doing something like this, try to get as much training data as possible for the first step in terms of labeling parts of the documents as relevant, right? If you do this, optimization becomes easier. You get a good sense of what the explanation is and what you should be using later on. Okay? Good. Let's go ahead. Now, we solved this. What do we get? We get the following. So, we looked at human annotations of fact-checking tasks. Remember, I talked about fact-checking. Fact-checking is you do an information retrieval task in the beginning, ranking task, and only have a look at the top 2 documents. And in these top 2 documents, you try to figure out parts of the text which are responsible for the decision. Okay? And it turns out that for this query, you indeed were able to figure out parts of the document which align with human annotation. Right? And this alignment with human annotations tells you, does this explanation align with what humans are thinking indeed are the reasons, right? This is called human annotations, human alignment. Okay? Sometimes these metrics are also called plausibility. People make a mess in naming metrics, by the way. Okay, so plausibility is the metric which is used in this sub-community, which measures how aligned are your explanations with the actual human rationale. Okay, this is not to be confused with accuracy. Accuracy is how closely is the explanation reflecting what the model is actually thinking about decision-making processes. Two different metrics. All right, okay. There are some benchmarks for this already. If you are interested in these rational-based tasks where you want extractive explanations and you can build this end-to-end models, right? There's a nice benchmark for this one. And the metrics are these metrics which look at human alignment, right? Which is basically a fuzzy matching between what humans have annotated and what the explanation says. But important point here again, human alignment does not mean that it is exactly reflecting what the model is actually doing. So it might be misleading metric only. So you don't only look at one metric, but you have to look at multiple metrics, right? And according to me, you should look at accuracy. In this case, this is accurate by design because it's only using the explanation to make a prediction, but you can never be sure. All right, so this is what I already told you. Now, how do you actually measure the faithfulness or the fidelity of the model? The faithfulness or the fidelity of the model is essentially what happens if I only use these explanations in the final output. Okay? And what people do is they use two metrics, and one is called comprehensiveness and one is called sufficiency. Comprehensiveness means that if you removed your explanation because you're selecting only a part of the text for explanation, right? If I drop this explanation, how much of the predictive power is retained by my model? If it is indeed the explanation, if I drop this part, right, then it should not, the prediction power should drop by a lot, right? And sufficiency is if I only use the explanation, what is the predictive power of the model? Right? So these are the two metrics which I used to figure out how important was your explanation towards the final decision making. One is comprehensiveness. If I forgot about all other features, that's sufficiency. If I forgot about all the features, and comprehensiveness is if I dropped the rationale or the explanation, what's the predictive power? Okay. Okay. So I talked about the problem of explain then predict models. These models, I mean, I like to call them explain then predict because you're doing explanation the first thing and the prediction the second thing. And I talked about a policy gradient way of optimizing this. In our work, we found that the policy gradient methods are extremely hard to optimize. Right? Now trying to answer your question more clearly, let's do the token prediction idea that you have. So what you can do is if you have training data, which is if people have highlighted parts of this input already, okay, can you do better? Can you kind of get better trade-offs between accuracy and explainability? Turns out that what you need to do is you can just simply turn this problem into token-wise predictions, whether this token is a part of the explanation or not, where you have the labels from the human annotations, right? Ask humans to annotate them, and you basically ask whether it's do a binary cross entropy over this one, right? Figure out if this token is a part of the explanation or not. And once you have the explanation, you just use the BERT model to make a prediction, okay? What helps here is that you would have seen that in this process, in the first process of doing explanations, it is completely unaware of the task. It does not know whether it's doing a classification task, a sentiment prediction task, or whatever, right? What helps is to make it task aware. So while generating the explanation, also train another classifier, okay, which is doing the task prediction in a multitask learning fashion. So what you do is you have the input here, right? You pass it through the feature extractor, which is BERT, and the output which you get can be used to in parallel train a predictor for the task and the explanation. And you flow the gradients in to optimize the gradients in this model, right? In this way, you're task aware. On one side, you're trying to optimize for your explanations, get the best explanation, but you're aware of what the final task is, right? And doing this in the multitask fashion really helps improve their presentation learning. Really helps it align to the human rationals. That's what we want, right? You want it to be right, but also for the right reason. This is what we started off with. So I will not bore you with the details, but you do multitask learning to have task-aware explanation generation the first step, and then you have the final prediction step, which is just a cross entropy. Now let's actually compare, right? What experimentally, what happens? If you use no explanation data and you use end-to-end classification, optimization, you see that, well, you get a point, I mean, the task performance is 0.83. In fact checking, 0.43 and 0.32 in all these three. Now, what happens is if you are task aware, okay, you actually improve in the explanation quality, right? You're more human-like because you have human annotations for this, right? So this is expected that you would actually be more human-like. But if you look at the task performance, and this is the interesting part, it's also doing the task very well. So if you need a favorable trade-off between task performance and explanation on human alignment, then collecting data actually helps, and doing this in a task-aware way helps even better. So that's the takeaway. There is a little bit of effort to get the annotations, right? But if you have more explanation data collected, you actually have a very favorable trade-off between, you don't, in some cases, we actually see that there is even improvement. I'm not going to use annotations on this one. So there is an improvement in the performance when you did not even, you did just the training on the training data without explanation data.
So the
Yes.
And also in the previous it's all the additive compound also that lambda probably selected.
That's just by validation, right? Just keep out some validations. That helps.
I'm guessing that depending on the value of the lambda does the task performance.
Yeah, it changes. But it's not that sensitive, right? So what actually is the killer here is the training data. If you get explanation labels. So later on, what we've tried out is if you only had small amount of explanation label, how does it actually affect? It turns out that explanation labels are very important, right? And they reinforce the task performance. So this is interesting. All right, okay, good. So now with these approaches, what you can do is you can not only get the explanation, you can not only get the prediction, which is that, well, this claim is wrong, but you can zoom into the part, why is it wrong? Okay. Good. So this is like some of our work, but there is also extensive work in the NLP community, which are called rational-based approaches. There is almost a survey on this. When it comes to ranking, it's very difficult to get label data explicitly for this explanation data, right? And here we found out that doing end-to-end optimizations also did not help, right? So here what we did was we did a little bit of optimization using the double max trick plus some relaxed subset sampling. The idea actually here comes from reservoir sampling. I'll not go into the details, but what we got was a very small set of terms result in big performance improvements. Whenever you have ranking models, the ranking models are only focusing on very, very small set of terms, 5 or 10 terms at the max towards making relevance assessments. And this is very interesting. Okay, so we talked about extractive explanations. Is this clear? Extractive explanations? Good. So let's actually go to a very interesting piece of work. And this is mostly done by Jonas, who's actually sitting there, right? And this is called probing. How many people have heard about probing? Wow, non-zero, which is good. Okay. I'm expecting good questions then. Good. So in probing, this is so until now we've talked about local methods, right? So you are given an input. How do I actually come up with an explanation for that input? right? But now if you want to holistically understand what the abilities of these models are, essentially figure out what are the abilities of these ranking models which make it good for rankings. You can take an approach which is called probing, which was invented again in the NLP community back in 2019. And what they did was they said that, well, I'm going to freeze the parameters of my transformer model, right? I'm going to freeze the parameters of the transformer model, and I'm only going to take the embeddings which come out of the text representation. In this case, if you have the following input, Dante was born in, and you ask what comes next, right? Only from the embedding of the input here, I can figure out if it understands world knowledge or not. Does it actually have these facts memorized or not? Okay, so this is how it all started. This is NLP, this is not IR, right? So what they're trying to look at is, can I classify a big set of tokens based on the input here, right? Basically mass language modeling kind of tasks. Okay? So now, how do we probe? So essentially what you have is, you have some input text, okay? And you have your supermassive transform model here. You freeze that, blue is for freezing, okay? And then you train a very thin classifier, thin meaning with small number of parameters, okay, to predict a property. Now that property could be anything, right? In this case, what you could say is that, hey, I want to know if the transformer model understands part of speech tagging. So what you do is you create for this property a small data set, and this data set is called as a probe task, okay? And given the output of these embeddings, okay, you train a classifier which will test how good are these embeddings succeeding in this probe task, which is answering my hypothesis that does it understand part of speech tagging? Okay, you can ask the same thing. Do the large language models understand world knowledge or the capitals of countries, right? You create a small data sets about capitals of countries, right? Use the embeddings of these models for these inputs and try to figure out if they'll be able to predict capital of countries or not. If they do, then you know that, well, it understands or memorizes or has this ability. Okay, this is the probing philosophy. So you have a frozen ranker in the IR case, and you have a question, and from these embeddings, you should be able to come up with the location. The important part to keep in mind here are your performance depends upon how good these probe tasks are, how good this data set is, and secondly, how small this probe model is. Because you would want to keep the probe model or the classifier as small as possible, because then you can kind of say that, well, all the decisions are actually taken, all the information is encoded in this embedding, right? And not in the probe model. This is two careful things for you to note. Okay, now, well, this is general probing, but how does it actually apply to information retrieval and specifically text ranking? So we do the following thing. We create some hypothesis. And our hypothesis is the following. Well, understanding BM25 is important for ranking. Surprise, surprise, right? So that's the, and according to that, we create a probe task, which is given a query document pair, it should be able to predict BM25, right? So the labels come from the actual BM25 value, and the input is just query document pairs. Second hypothesis, understanding or spotting entities is important for retrieval. Okay, we create a similar probe task or similar data set, right? And similarly, we make all these probe tasks, one on semantic similarity, one on co-reference resolution. This might not be obvious, but we'll just keep that in play. And then we look at the embeddings, and not only the embeddings at the last layer, but we look at all the intermediate embeddings and see if these embeddings contain enough information for us to make some progress in the probe task, right? If they're able to have good accuracy in these probe tasks, that means that they have this ability. Okay, at this point of time, I'm going to ask, what do you expect for BM25? Is BM25 useful? Is it useful at the last layer? Is it useful in the middle layer? What happens? Any speculations? The setup, is the setup clear? I'm only going to use the embeddings of the input to detect if the model actually has one of these abilities. And for each of the abilities, I have a training list. Does BM25 help? Who says no? I'm very happy that nobody is saying no. Who says yes? Good. Who says that BM25 is equally useful in all the layers? Who says that BM25 is useful only in the last layer and doesn't matter in the intermediate layers? Okay, you're in for a surprise. What we found out was the following, and this is for BM25, I think. So what we found out that in the beginning, most of the word ranking models did not have all these IR abilities, right? Or the hypothesis that we kind of went on to ask. And in layer 4 to 6, they have the maximum performance, meaning they were able to correlate with BM25. So they understood matching in the intermediate layers. Okay. But then for the final task performance, the prediction accuracy dropped. Now, what does it mean? It means that it is learning. You need to understand matching. It's like edge detection in an image classifier, right? You need to understand the structure of a face where this is, right? So BM25 is a very important building block towards something which we still don't know, which these models are still learning, towards coming up with better relevance estimation. Okay, you might not need BM25 that much at the end, right? But well, BM25, all of the plots for all of the methods have a similar trend. Okay, so the task performance in the last few layers, it forgets about making it good for BM25 or all the other ones, right? It is optimized for task performance in the last layers here, but the intermediate representations actually encode all these nice IR properties. By the way, this is no conclusive evidence, but this is the first step towards showing that they need lexical matching. So recently we've done some work which try to figure out whether this is just correlation or whether there is causal evidence that learning BM25 actually matches. So stay tuned. Okay, so I want to at least spend 5-10 minutes on challenges and open problems, right? Because all work and no open problems make it a dull day. I see questions there.
We'll go back to the how you actually code the protocol.
Yeah.
So, I mean, naturally, query separator document makes sense on its process code
Yeah.
BM25, but how do you make a problem task with name density resolution in the same style?
So what you can do is, and you will correct me if I'm wrong, right? So what you can do is for the query, you can go and annotate parts of the document with name entities, no? That you can do this in a pre-processing manner. You can use Stanford Core NLP and go and annotate parts of named entities in the query and as well as the document.
But then that model itself, like you could use a query document style for named entity in the first place. So you might be encoding things that are not part of the.
So what happens is that let's say that you use the same input to one of them, right? And the embedding that you get is fixed. For all of them, the embedding is the same for all the probe tasks. Now, each of the tasks is different, right? So you set up the task with different classification problems. I can explain this to you a little bit later, right? But what happens is you take the embedding input, right? And use the embedding input to annotate parts of the text.
But the embedding input itself was not targeted towards, and like I understand the probing mechanism.
Yeah.
But it's unnatural to expect an linear capability to be embedded in a query document embedding. If it was in a bytecode, yes, but in a cross-encoded setup, this is a bit counterintuitive, but BM25 makes more sense. But then,
Okay, so
like, they
let's- I would say that both of them are actually equally have the same philosophy, right? So assume that it understands named entity spotting. Assume that it does that, right? So what does it mean? That the attention heads over the named entities will actually get more mass, right? So they will actually pay more attention. So the entities in the query will focus on the entities of the document, isn't it? So the feature representation, the feature extraction which happens will happen on this attention masks, right? So the final embedding which you get for a query embedding pair, right, will be based on the increased attention on the entities or entity in the query and entities in the documents.
It's a bit of a loose probing definition compared to the original standard of taking an embedding model and seeing the embedding model, because there is the task pre-cooked essentially in the text. That's what I feel like there is.
Okay, so you mean that, well, in the original probing definition, you were doing the masked word prediction, which was clearer, and in this case, you're just taking the embedding to do some classification, which is a kind of ill-formed definition. Is that what you're saying?
It's hardly that for IR, I see it, but it's losing the original part of.
Yeah, I mean, okay, so we take the philosophy of probing, but we kind of adapt this for information retrieval. Yeah.
But there is a mismatch. Well, I understand it's fully for BIM25. The other tasks,
Okay,
I'm a bit more skeptical to accept them fully.
okay, fair enough.
In the next slide, you were showing that a fourth layer or something. Right?
Yeah, it depends upon different tasks, right?
Yeah,
For
so
example,
this is the regular size word, right? Well,
This is full layer,
well,
yeah.
Have you played around with large? And
no, unfortunately not. No.
micro word or something?
No, we have not.
Because my question was then, let's say, I was thinking that if you take the fourth layer out.
Yeah.
That is kind of like a supplement for parts and then you have 25
Mhm.
How does it, so if I take, let's say, a 4-layer word,
Mhm.
does it more closely maybe get 25 spots embeddings, or is it like maybe if I take a smaller word, it will be in the earlier layer than the smaller? So that's my question.
Interesting question, actually. I do not know, because we've not experimented with smaller birds.
My question was.
We have not, right? Or have we?
I actually did.
Oh,
It
great.
turned up in the paper. So I played around with 6-layer word models.
Yes.
And you would actually see that stuff would get moved to the left.
So
So
Meaning earlier?
Earlier.
it's
Earlier.
basically compressed in a way.
Yeah,
So maybe the second layer in the 6-layer word and.
could be.
Okay.
But the operating principle is that you actually need to learn,
Yeah,
these
yeah,
models
understand.
actually have to learn matching to build representations on top of that. So we've now done this on dual encoders also, but that's a different discussion. Want to go to open questions? Yeah, so critical view on evaluation, right? So I think that evaluation is actually one of the Achilles heel of all the interpretability research, right? More work needs to be done. Some ideas about how people do evaluation right now. It's very difficult to evaluate or get ground truth for the approach, right? So for post-hoc explainability, you would want to know what is the innate decision-making process. And well, that's exactly what your goal is, right? So it's very difficult to kind of, make progress here. But some of the approaches there is that include a shortcut in your training data and make sure that the shortcut is taken up by the machine learning model, okay? And the shortcut essentially then becomes the ground truth, which you want your explainability model to surface, okay? So that's one approach. The second approach is use a simple black box. I told you about internal query expansion techniques, right? Why not use RM3, where we exactly know what it is internally expanding the query to, right? And then use as a ground truth. But the problem with these evaluation approaches is that, well, it might be good to evaluate under these conditions when there are shortcuts, or it might be already very good to explain simple models. But in reality, it's very difficult to kind of replicate that, right? Maybe it's possible that explanation methods work only for simple models, but not for complex models. Or maybe it's very good when it's very confident when you have shortcuts, but maybe not in the real world, right? So these are some of the limitations. None of the this general lack of benchmarks for evaluating explainability methods. There are some, ERASER being one of them, and people do a lot of human studies, and this is where you have to take all these approaches with a pinch of salt, right? Which is that, well, some explanations that are understandable to the human does not mean that it is explainable. What you want really is that the explanation should be faithful to the model's decision making, and that's usually hard to evaluate. But please don't stop accepting papers or working on explainability. I have a very interesting story here. I went on a 2-minute rant in Sigaya of this one, right? So you should understand the challenges of explainability and evaluating. And well, some of the reviewers I think took offense. No, they did not. The entire frame in Sigaya, there was a big screen here. It started falling on me here. Exactly on this slide when I finished my rant. So I decided not to talk about it. Right? So, well, it's a difficult problem, but that's also an opportunity for all of you to work on. It's a very important challenge. I think many people shy away from the problem of evaluation. We as an IR community are very strong in evaluation. We have a good culture of evaluation, and we should attack these problems head on. Okay. Well, a glimpse into the future. We know that large language models are here, and there will be more in the future than less. I would say that we should strive towards making explainability as a first-class citizen already during building our models, right? In cases where it is possible, as I mentioned in the intrinsic explainability approach, we should try to collect as much explanation data as possible, whenever that's possible, right? In many learning to rank situations, it's not possible. But in case of relevance assessments for text data, maybe it is possible. Maybe it's also possible that you collect only a small amount of training data. There is science to be invented about how much training data do you need to collect in terms of human labels, and what is the strategy of optimizing for the budget of training data, right? There's a lot of science to be invented there, but that should be our first line of action, right? In case when it's not possible, you should actually try to have as much human interaction while training, right? You get some you have some post-hoc approaches. Can we come up with methods which can inform the model developer where things might be going right? So you have nowadays what you do is your training set, you have a test set, you look at test accuracy, hurrah, right? No, right? You should kind of go back to instrument parts of or try to figure out what are the shortcuts that these models might be learning, and explainability tools might be one part, right? So I would say that use explainability with human involvement if possible during model development process. In the age of LLMs, this is what people keep asking, right? People say that, well, they're becoming more unexplainable. But I would actually say that what you can do is you can actually add the human closer to the querying process to get training data to improve your information retrieval system. Now, how is it done? So assume that you have a query. Let's say that this is a really ambiguous query DNR. You do not know anything about it, right? And then the query rewriter here, you have a query rewriter, and that could be a large language model, and that will basically expand this query into a more natural language processing. Do you mean do not resuscitate orders? And this is something which you can show it to human. Okay? And what you get is you get human evaluation immediately, which will then improve the final document ranking task. Now, what's happening now is this query rewriting is happening internally. You have the document ranking, and you have interaction at the rank list at the end, right? You have yes or no, all these query logs at the end. Now, that's very, very far away from the actual querying process. That means optimization is hard. You have to come up with ideas about how do I denoise it, what is noise, what is not, and so on, right? If you have user interaction very early on here, and maybe LLMs are actually a good way to do this, you get cleaner training data, you get more user agency, okay? and it can help you design better retrieval models. Now, by the way, this is nothing which is extremely new, right? All these ideas have been there in information retrieval for a long time, right? But now with the LLMs, you can train these LLMs to kind of generate this better query rewrites. Okay. What you can also do is you can actually ask these outputs to be edited by the user, right? So the user does not have to refire the query again. So you want to reduce the number of explicit query rewriting by the user, right? And in many cases, you can also ask the user to kind of explore more, right? You can actually have a much richer set of query rewriting techniques using LLMs, which means that more agency to the user. Okay, in conclusion, so what I talked about is I talked about notions of interpretability, how to evaluate them, what explanations, who the explanations are for. We looked at two separate kinds of explanation families, post-hoc and intrinsic models. We also looked a little bit into proving about general abilities of IR models. And finally, we had a look at some open problems there. That's it. There is a nice survey. Have a look at it, right? We are continuously updating it, not as frequently as I would like to, but it's still there, right? Thank you. And questions?